Welcome everybody to today's Heidelberg Joint Astronomy Colloquium. And we have today Professor Marta Volonteri here as our speaker, and she started her academic career with a PhD in astronomy at the University of Milan with the advisors Professor Madau and Professor Hart, and then moved on for a postgraduate researcher at the University of California in Santa Cruz. And then made several postdoc stops, one in Cambridge, UK, and then into Ann Arbor. And then came to the Institut d'Astrophysique de Paris in Paris, in France. I hope I pronounced it well. And right, where she now is it's called Directeur de Recherche. And so she's there, a full-time research position there. And today, she's gonna talk about the growth of massive black holes. And I would like to welcome her here to Heidelberg. A little bit lower.
Okay. Good evening, everyone, and thank you very much for inviting me here. It's really a pleasure, and it's been fun to talk with a lot of people during the last 2 days. Today, I will give you a brief, broad introduction on the growth of massive black holes, focusing mostly on the RHT universe. And this is work actually mostly done by some postdocs, Gillian Bellovery, now at Vanderbilt University, Pedro Capello at the University of Michigan, and Johan Dubois at the Institut d'Astrophysique de Paris. So when I talk about massive black holes, let me first discuss a little bit what I mean by that. So we all know about stellar mass black holes. They exist throughout our own galaxy. Their masses are up to a few tenths of solar masses, and we also know very well how they form. They are the end point of the lives of massive stars. Now, these are not the black holes I will be talking about. My favorite black holes are massive black holes that were first hypothesized for powering quasars, and this year we actually celebrate the 50th anniversary of the discovery of quasars. And later on they were confirmed to inhabit the centers of many galaxies, including our own Milky Way. In general, the masses of observed massive black holes are above 10 to the 5 solar masses. So you see here there is a huge gap in masses between the stellar mass black holes and the supermassive or massive black holes that we see in galactic centers, which is hinting at very different formation paths and evolution scenarios. So our current idea of what the relationship between black holes and galaxies is can be shown as a series of scales. Now let's start with this cartoon of a galaxy similar to the Milky Way. I put here some general scales. Here we see in the galaxy the dark matter halo, the galactic disk, which is made of stars and gas, and the central bulge, mostly made of stars. The masses, so for say a galaxy like the Milky Way, is about 10 to the 9, 10 to the 10 solar masses in gas and stars, and the dark matter halo totally is about 10 to the 12 solar masses. We can characterize these objects through their physical sizes as well. Using just simple scalings, the dark matter halo size scales with the mass of the dark matter halo and the velocity distribution of stars, which is an indication of the thermal motions of stars. And this size is about megaparsec scales. Then if we go, for instance, to the bulge, down here, the mass of the bulge is typically about a factor of 1,000 less of the dark matter halo. This is just to give you an idea of scales, don't take it literally. The velocity dispersion is similar for dark matter halos and bulges, so you get that these scales are of order of kiloparsecs. Now, this is what characterizes a galaxy. But when we go to black holes, we really have to zoom in by several orders of magnitude. When we think of black holes, we can define 3 characteristic scales that define their environment. So the Bondi radius is the radius within which the black hole dominates the dynamics of gas. and it scales with the mass of the black hole divided by the sound speed squared. The mass of black holes in the center of galaxies are typically between 10 to the 5 and 10 to the 9. And again, as a rule of thumb, you can think of a black hole mass as being a factor of 1,000 to 500 times less than the mass of the bulge. The sound speed is between a few tenths to 100 kilometers per second for most galaxies. So immediately you see that the scaling, once you have here the black hole mass and the sound speed, leads you to a scale of about parsecs. Similarly, we can define the sphere of influence. This is the region within which the black hole dominates the dynamics of stars. Basically, inside the sphere of influence, the potential is Keplerian. It's just determined by the point mass, which is the black hole. Outside, the potential is determined by the distribution of stars in the galaxy. And again, this scales with the black hole mass, velocity dispersion, the same pretty much that we had up here, again, order of magnitude, and this becomes parsec scale. Then we have another scale, which is the Schwarzschild radius of the black hole. This is the radius at which the escape speed equals the speed of light. So again, it scales with the black hole mass, but now at the denominator we have the speed of light, which is much higher. And so this is a scale of about microparsecs. So when we study, and this is what we're doing right now, the evolution, the formation of massive black holes in galaxies, we really have to connect this very wide range of scales, trying to connect the physics of black holes to the physics of galaxies, and how they evolve together, as we will see, over 13 billion years of cosmic evolution. So in this picture, this is actually, so first of all, notice that this is not in scale. But this is, if you think of it of a Milky Way, we know that at the center of the Milky Way we have a black hole. The mass of this black hole is about 4 million solar masses. The black hole in the Milky Way has the characteristic of being a very quiescent black hole. So if you study this black hole and you measure the luminosity that you get out of it, the luminosity that you get out of accretion of material in it, the luminosity, the typical luminosity of this black hole is about 10 to the 34 ergs per second. You can compare this to the luminosity of the sun. It's just pretty much the same order of magnitude. So there are some black holes in the universe that are extremely quiescent, dark, black holes. But then you have the other extreme, which are quasars and AGN. In this case, again, you have a black hole, but it is accreting matter at a very fast rate. Matter is crossing the event horizon and is going to increase the mass of the black hole. At the same time, some of this mass is radiated away. The luminosities of quasars is as much as an entire galaxy, 10 to 11, 10 to 13 solar luminosities and more. However, as we have seen, the size of the emitting region is much, much tinier than the galaxy. So these are objects that are extremely powerful at converting matter into energy. Now, in fact, in 1963, this is the way first it was proven, or actually hypothesized really, that in the universe there are black holes with masses of millions to billions of solar masses. We see these black holes throughout the universe. This is actually M87, which is very nearby. You see here a nice jet coming out of the central black hole in this elliptical galaxy. Now, we have seen the black hole in the Milky Way, which is really the closest massive black hole that we could possibly imagine. We see M87, but then we have objects that are much more farther away. This is a compilation of redshifts of high redshift quasars compiled by Zhao Fan in last year. And you see, you can read here the names and the redshifts of the highest redshift quasars at that time. Here they start at redshift 6 and they go all the way to redshift 7. So this is really very far away from us. In fact, this proves that there were massive black holes, there were quasars when the universe was very young. You can see here cosmic time, the age of the universe, is a function of time, and here each dot represents a quasar. Now this already shows you that they exist when the universe was young, But it's very clear what I mean by a young universe when we put it in the context with the age of the universe today. So today we are here at redshift 0, 13.7 billion years, and the quasars that I'm talking about existed when the universe was really less than a tenth of its age today. When we think of the evolution of the universe, typically we think of a cold dark matter universe in which things start small and they grow with time. So if we go back to early times, we imagine objects to be smaller than today. Well, this is not the case, well, partly because we can detect only very massive luminous objects at high redshift. But if we focus for a minute on the current record holder for the highest redshift quasar, as I said, redshift about 7.1, the mass of this black hole is about 2 billion solar masses. Now, I told you just a few minutes ago that the masses of the black holes that we know today go between 10 to the 5 solar masses to a few times 10 to the 9. Actually, now we have some black holes in nearby galaxies which are a few times 10 to the 10 solar masses. Here, this figure shows the mass of a black hole as a function of the velocity dispersion in a galaxy. And you really see that today we probe black holes in a wide ranges of masses. Now, if we put this quasar at redshift 7 on the same scale, it sits right there. So it is as massive as some of the most massive black holes that exist today, but when the universe was much younger. So the typical analogy that I give is to find a child who is 180 centimeters tall, but is still in kindergarten. This is the type of objects that we're studying. So we can find some information about their formation, their growth, from what we know about them. We don't know that much, but we still have some information, especially I will focus on this particular quasar. And what we can assume is that this black hole formed at some point in the universe, well before being observed, so at redshift higher than 7. And then it started evolving with its own galaxy, but in particular it started growing in mass. Whenever a black hole is fed some gas, it starts accreting and growing. It swallows this gas. And typically, under most conditions, we assume that the luminosity of an object is Eddington limited. So the radiation pressure from the quasar or from the star, this is the same physics, does not overcome gravity. Now, if you think of the opposite case, when luminosity is super Eddington, the radiation pressure from the quasar or from the star will push away the material instead of letting it fall onto the black hole and let it grow in mass. So by taking this assumption, if you assume Eddington limited accretion, it's very nice because it gives you a very simple closed equation to grow the black hole in mass. It's a simple exponential growth. Here, the information you need is the initial mass of the black hole. And then here you have some parameters. One is the time. So you let this initial seed grow for a time t, and you find its mass. And here you have two extra parameters. One is epsilon. It's called the relative efficiency. It's the fraction of mass that is radiated away as energy. So it determines the luminosity of your object. And then you have this f-ed. It's called the Eddington ratio. If the Eddington ratio is 1, you are accreting exactly at the Eddington limit. The Eddington ratio less than 1 will be a slower pace of accretion and growth. So once you have this very nice closed equation, you can just rearrange the terms and cast this in terms of growth time. So you start from initial mass m0, you want to grow to a certain mass m, and you have this simple relationship for the growth. So the typical time scale you see here scales with 0.45 gigayears, which I usually call the Eddington time scale. Now, for this quasar at redshift 7, we have some information. I told you that the mass is estimated to be about 2 billion solar masses. The other information that we have is that the maximum growth time is the age of the universe at redshift 7, which is about 0.75 gigayears. So what we get out of this? Well, we know at this point that the ratio between the growth time and the age of the universe is about 0.6 modulo these factors. Now, we also estimate this mass at Redshift 7. So in other words, we can say that we have only 3 unknowns and variables in this. One is the initial mass of the black hole, the initial seed mass called m0 here, the typical Eddington rate, so how fast the galaxy is able to feed the black hole with fresh gas, f_ed, and the typical radiative efficiency epsilon. Now you can see directly from this equation that the dependence on the initial mass is only logarithmic, so it's very mild, and you have more direct dependencies on everything else. Now, sure.
Why is the typical Eddington rate rather than the maximal? Because these objects are so rare that clearly that's not the typical thing.
Exactly. So in this case, I will assume for the moment, so here you can assume that the Eddington rate is 1. And then I will discuss some analysis, some simulations, and analytical models that predict what is the typical accretion rate for the average black hole and for these beasts. In fact, I will go in turn and discuss first initial seed mass, then I will discuss how galaxies are able to give gas to the black holes, and finally I will go into something a bit more exotic and discuss the typical radiative efficiency. So let me start with the initial seed mass. Now, let me start with this talk. I will discuss many theories. I'm a theorist. But I will not give any answer. These are all things that we're studying right now. So let me start with theories for the formation of massive black holes in high redshift galaxies. Now, this all actually dates back to an original paper by Martin Rees in 1978. It's almost 40 years later, but the type of physics that we consider is still very much the same. We have just eliminated some possibilities. Now, the way I typically discuss this is imagine that you are looking at a high redshift galaxy. This is nice because high redshift galaxies are in some sense simpler than today. They were smaller, they were composed mostly of dark matter and gas. So we can think of it as a time where stars were not dominating yet the universe. So a galaxy for the next 5 minutes or so will be a big ball of dark matter with a 10%, 15% gas fraction in it. How can you take this system, this physical system, and create a massive black hole in the very center? I will describe here 3 particular ways of doing that with pros and cons. The first one relies on the very first stars. So now this, for many years, this was proposed in 2001. And this is a very nice, natural way of forming black holes because the physics is the same one that we know for stellar mass black holes today. We just change a little bit in the sense that we're looking at the universe before the first stars were born. So a universe that is metal-free. You have only hydrogen and helium. In this case, when you have no metals, cooling is particularly slow, which means that you don't have strong fragmentation and efficient star formation. So early simulations of star formation in these conditions, so very high redshift, no metals, suggested that the first stars were massive, up to several hundred solar masses. Now, this was very appealing because stars that are metal-free, 0.1, and 2, very massive, with mass larger than about 250 solar masses, are predicted to collapse into a black hole with a very small mass loss. Now, if you think of, for instance, changing one of these issues, for instance, you go to solar metallicity, this doesn't happen. A very massive star has several mass losses through winds. You think of it as a red giant. And the final black hole mass will be much smaller. But at zero metallicity, you retain most of your mass. And the final remnant has a mass which is similar to the mass of the initial star. This was all very happy and nice until a few years later, there was some revision on the initial mass of these stars. Instead of being 100 to 600 or 1,000 solar masses, now they're expected to be much smaller, say a few tens of solar masses. Now, suppose that you are here in this galaxy, which is as a rule of thumb, you can think of the total mass of this galaxy to be about 10 to the 6 solar masses, so very tiny compared to today. But still, if you put a 10 solar mass black hole inside a galaxy with a mass of 10 to the 10, it will be very hard for this black hole to find its way through dynamical friction to the very center. So you create a relatively massive black hole, about 10 solar masses, that is sitting in a galaxy and doesn't know where to go. So this has become a bit of a problem. And so in the last few years, there have been efforts to study in more detail other ways that you can take the same initial conditions and create a black hole out of them. In particular, a second way to form a black hole in there relies on what we call global dynamical instabilities. Now, take again the same galaxy, dark matter and stars. Now, if this galaxy is not stable means, for instance, that you have not enough rotation, so that you cannot sustain energetically the gas in that galaxy, the gas will start to contract and condense. The gas must be able to cool, of course. But when you are globally unstable, in a deep potential well, you want a potential well which is very deep, so you can condense gas. If you are globally unstable, in these very rare galaxies, what you have is a global inflow of gas that brings several 10 to the 6 solar masses of gas within the central few parsecs. You create very, very high densities. And at this point, you may actually be able to form a black hole. There is one thing you have to fight against, though. Star formation. In particular, if you have, again, think of this total mass of this galaxy is about, this point, 10 to the 8 solar masses, including dark matter. If you calculate the binding energy of this galaxy and you compare it to the energy of a supernova, you find that they are similar. So if you have even only one supernova going off, while you have this collapse and condense gas, you may blow away most of the gas and be left, well, without gas to form stars and not to form a black hole either. So, yes?
So when you talk about global dynamical instabilities, you are talking about gravitational instabilities?
Gravitational instabilities, yes. Globals, not local. So you don't typically describe them as a Q parameter. The Q parameter is too mild for that, yes.
But also you need some cooling, right? Because you need some cooling.
Absolutely, absolutely. Yeah. So you need enough, so the halo must be able to cool. So if you're at zero metallicity, you may want to have atomic cooling, atomic hydrogen cooling, so temperatures above 10 to the 4. Or if you have metals, cooling is not a problem, but then you have to fight with star formation. So in fact, the whole point is that these dynamical instabilities, these gravitational instabilities, must occur and bring the black hole formation process to an end before the first star supernova goes off. So it must be a very fast, efficient process. What happens at that point? So you're collecting gas. So suppose that all these features are met. You're collecting gas. This gas is falling in very fast, let's say at a mass inflow rate larger than about 1 solar mass per year. Now you're growing, this mass is going towards the center, it's increasing density, and at some point you start having the conditions to form a star. Now this is a condition in which the inflow rate is so high that the star that you're forming never actually reaches stability. You have nuclear reactions that occur throughout the process, but still the push from the outside, the gravity from the outside is much stronger. Very quickly, you have core collapse. Again, it's a normal superstar. It's just that this star can reach masses of about 10 to 6 solar masses or so. At the very center, you form a tiny black hole, just core collapse, neutrino cooling. At this point, you have formed a tiny black hole, about 10 solar masses, surrounded by what is called a quasi-stars in lingo, which is falling, raining down onto the black hole. Now, the black hole does what it's good at doing, accreting mass, accreting material, and it can do it at very fast rates. So I told you just early, 2 minutes ago, that there is this Eddington limit. So you don't expect luminosity to be larger than the Eddington luminosity. Now, in this particular situation, what you actually get is that the Eddington limit does not apply to the mass of the black hole itself, but to the whole envelope surrounding it. So you are allowed to accrete at Eddington rates, which are about a factor of 1,000 higher than the Eddington rate for the black hole, and it can grow in mass very rapidly, in about 10 to 3 years or so, to reach masses up to 10 to the 4, 10 to the 6 solar masses. Now, this is a very appealing way to form black holes because you see here, they start pretty massive. In the case of POP3 stars, the first black holes were at most hundreds of solar masses. Here you get up to 1 million solar masses. But as I said, this is a rare process. With the bottleneck being this phase of the global dynamical instability.
So you say that you can sort of circumvent this Eddington limit. Is that because in this case you have almost zero radiative efficiency? Or something?
Well, the radiation is the radiation is trapped, which you can express this as a very low effective radiative efficiency. So sorry. Yes, yes. In spherical symmetry, everything is easier, isn't it? No, yeah, it's true. Radiation is trapped very easily in a spherical symmetry. As when you have disks, it's much easier for radiation to leak out. I agree with you. So here we assume spherical symmetry. Okay, so as I said, this is, as we just discussed, this is a process that is very good at forming very massive black holes, but it's very difficult to reach all the conditions. So you expect this to happen very rarely, in 1 every 1,000 or 10,000 galaxies. What happens in other galaxies? Here we go back to what we were discussing a few minutes ago, which is local instability, what we typically refer to as the Tumre parameter. In this case, again, the same galaxy, well, not really the same galaxy, again, a high redshift galaxy in which you have global stability, but local instabilities. Local instability typically means that you are forming stars. Gas is fragmenting. Now, if you are on the verge of stability, so if you are at the critical Tumre parameter, gravitational instability can lead to mass inflow, basically redistribution of mass throughout the galaxy, rather than global star formation. In this case, you are having an inflow of gas towards the very center of this galaxy. Now, if you are creating an inflow of gas, which is not in this case as dramatic as before, you don't have 1 solar mass per year of inflow, but something much smaller, you are anyway increasing the central density of your protogalaxy. If you increase the density, it makes it much easier to form stars in the very center. So what you create is a very dense star cluster at the very center of this galaxy. This star cluster has a mass of about 10 to the 5, 10 to the 6 solar masses in parsec scales or so. So this is a case in which you start forming stars, the first stars that form among the stars, you will form some very massive stars as well. Gravity acts on these stars. The most massive stars migrate towards the center of this very dense cluster. It's very dense. There is not much space. Eventually, these massive stars that sink to the center are bound to collide and form a more and more massive star, just by the merger of these other stars. The very massive star that forms in the center can be up to about 1,000 solar masses or so. And at this point, the key here is if you are at low metallicity, star doesn't actually go into a red giant phase. It doesn't go into a mass loss phase. And so it can collapse again into a massive black hole, which is expected to reach masses of about 1,000 solar masses. So summarizing these processes, going back to this table slide, you can start from pretty much the same object, a galaxy at high redshift, and through different processes, create black holes in the center. Now, here I reported the masses of the seeds from 100 solar masses in the case of POP3 star remnants to about 10 to the 5 solar masses for the case of dramatic direct collapse, to about 1,000 solar masses for the case of local instabilities. Now, what I haven't reported here are the efficiencies. We expect this process, if it happens, it's rather common in galaxies. This process is a bit less common, and this is really the rarest to happen. But the one thing that I want to focus on this slide really are the masses, and go back, once we have this information, to my little estimate of the growth time for the quasar at redshift 7. So we were saying we have this equation, the unknowns are 3, and one of these is the initial mass of the seed. So again, let's take this quasar at redshift 7, the mass is larger than about 10 to the 9 solar masses. Let's take the lowest limits that we have on the relative efficiency. The relative efficiency in a standard relative efficient accretion disk is determined by the spin of the black hole only, and it's 0.06 for a Schwarzschild black hole. So let's take this value. It is up to 40% for a rapidly rotating Kerr black hole. But you see here, dependence on epsilon is such that the lower is epsilon, the easier it is for the black hole to grow. Let's take the maximum limit on the Eddington rate, 1. Now, let's assume that these initial seed masses from about 100 solar masses to 10 to the 5 solar masses, and find the ratio of the growth time to the Hubble time at redshift 7. And you find that being very optimistic in your assumptions on the masses, but especially on the accretion rate and the relative efficiency, you get that the growth time is about 40%, which means that this object must be fed at the exact maximum rate, Eddington rate, for at least 40% of the time. So for half of its lifetime. And here it starts at redshift infinity. So this gives you an idea of, as Hans Passer was saying, of how hard it is to grow these black holes. Not only you have to make them early on, but you have to feed them as fast as possible. Now, a duty cycle of about 40% is a duty cycle of unity, which is extremely rare to have. And I will show you why it is extremely rare. Because this is a mathematical limit. This is just an equation, right? But then when you put the conditions of your galaxies and you try to see if they're able to feed these black holes, then you find that you're really in trouble. Sorry, Dave?
I don't understand why you're troubled by a unity duty cycle.
Oh, I will show you. That's where I'm going to.
Clustering of quasars at high redshift suggests that their lifetime is the
whole time. Well, all these arguments suggest so, but the problem is now you take a galaxy and you have this galaxy to feed 10 to the 9 solar masses within a parsec in that time continuously. So I'm not talking about statistical constraints. I'm talking about the ability. What I want to know is how a galaxy is able to do that. So, and that was. We know that they exist. I mean, we know, but we have to understand how they got there. I mean, it's not a problem of counting. So, exactly. So we are going to feeding and feedback in high redshift quasars. So as I said, they require very efficient, almost continuous accretion at the Eddington rate, which means that first, the galaxy must be able to supply about 1 solar mass of gas per year for about 750 million years continuously at the whole time, or at least half of this time. And second, when the supply of gas is available, you're feeding the black hole at the maximum rate. What happens with the radiation and the kinetic energy that is coming out of this quasar? I told you about this Eddington limit, which is a simple description. When you have too much radiation, too much energy coming out of the center, you're affecting the properties of the galaxy itself. So this is not a problem that you can decouple. You have to put everything together. So the way one can study this is to use numerical simulations. In particular, what we used were zoom-in cosmological simulations. So we start from a box of the universe, a large enough box. We let it go all the way to redshift 0. Here it's just dark matter. Then we select a patch of this universe, and what we want is to resimulate it at much higher resolution, so that we actually can trace the inflow of gas towards the black hole. Not really into the black hole, because remember that the scale of the Schwarzschild radius is 10 to the minus 6 parsecs, and the whole box is several megaparsecs, so it's currently very hard to study everything together. So we take this patch of the universe and we resimulate it at higher resolution. This is a galaxy. This is not a super duper high redshift galaxy. It's more like our own Milky Way. but it gives an idea of the processes that are happening. Here you're seeing streams of gas. Here green is gas. Stars as they form are blue, and they turn red as they age. So you can really follow the growth and formation of galaxies and of the embedded black holes in these galaxies as a function of time for many billion years. So as I said, this is a galaxy like our own Milky Way. It's just it was the prettiest movie that I had. But the evolution in a higher redshift galaxy is even more dramatic. You have more mergers. You have many more galaxies in the same region. But what I would like here to stress is what is going on. Here you have streams of gas, these green filaments. You have mergers between galaxies. You have star formation. You have all the processes going on at the same time. Now, as I said, this is a Milky Way type galaxy, so there are not that many mergers occurring. You see here that you have formed a nice bulge, and then you are recovering your stellar your gas disk as a function of time. Now, this is the type of technique that we use to study where gas goes to and from. And I will explain to you what I mean by to and from in a minute. This galaxy is going on for another billion years like this, so I will stop it here. We have a dinner to go to. Okay, so now, the beauty of having a simulation like this is that you know, you can run it forward in time, you know where gas is going to, but being simulation and not being a real life and a real physical experiment, you can actually turn back in time. Or in other words, whenever you see a parcel of gas that is accreted on a black hole, you can ask yourself, where was it coming from? So we trace back the provenance of this gas, asking where it was coming from. And we compare the way black holes get their gas to the way galaxies get their gas. So we have seen the evolution of this Milky Way. We haven't seen the black hole in there again because it was too tiny. But we can make an analogy between the way galaxies get their gas and the way black holes get their gas. So let's start with galaxies. It's simpler. How do galaxies get their gas? So if you have a galaxy, typically if the mass of the galaxy is large enough, sorry, I'm not used to all this technology. So usually when you have a large enough galaxy, the galaxy is surrounded by dark matter halo, the virial temperature is sufficiently high that when the gas crosses the virial radius, it shocks and becomes very hot. So this hot gas will be highlighted in red throughout the rest of this talk. So this gas enters, becomes shocks, is very hot, is typically not very dense, and eventually it will rain down to the disk. However, low-mass galaxies have virion temperatures low enough that gas does not shock when it enters the dark matter halo. So you have cold, diffuse gas surrounding your galaxy. And then if you think of the movie that I just showed you, you have a third way to get gas to your galaxy, through these collimated streams that really go through the shock and feed directly the disk, not the black hole, the disk of the galaxy. The black hole is 6 orders of magnitude inside that. Okay, so we take this and we go, let me skip this movie, which is, I will go back to this movie later on. And again, thinking of the movie that we saw earlier on, the green one, we have seen that galaxies merge together. And when two galaxies merge, you will form a larger galaxy. But this gas, interestingly, during mergers, tend to deliver gas very close to black holes, very close to galactic centers through tidal torques. And let me show you another movie of a merger simulation. Here, what I want you to focus on, these are just two normal spiral galaxies merging, nothing exceptional. But just focus on this flickering in the center. Here, this flickering is proportional to the luminosity of the black hole in the center. This is a simulation that has a 10 parsec resolution, so we're really getting close to the sphere of influence of the black hole. And you see that here, you have early phases in which the galaxies behave in a quiescent way. The black hole is flickering anyway. So if I go back, you see here that the black hole is flickering also at early times when there are no tidal torques. This is stochastic accretion. But then when you get to very strong dynamical inflows triggered by pericentric passages like this, you have gas inflows that feed directly the black hole. So, well, this is explanation. So you have tidal forces that go all the way to the center. You lose angular momentum. So in this plot here you have various information, the distance between the two galaxies, the luminosity of the two AGN, the specific angular momentum, and the gas mass within 100 parsecs. And now what I want you just to notice here is the connection between AGN activity and angular momentum losses. So this is really what I mean by merger-driven accretion. Now, we have seen that all these processes, cold flows, hot shocks, mergers, occur throughout the ages, the lives of galaxies. But now the next question is, what is the dominant mode to grow black holes at high redshift? So as I said, we trace backwards the growth of black holes, asking where this gas is coming from. And the color coding is as before. Cold is shown in blue, and this gas that is accreted on the galaxy directly being cold, so 10 to the 4 Kelvin and less. Shocked gas is hot gas that typically you have when in massive galaxies. And what we call clumpy accretion is gas that is accreted through galaxy mergers. Now the galaxy that I'm showing you first is a normal galaxy. So, as we were discussing earlier on, we have these super duper massive black holes at redshift 7. Now, this is not one of those. If you read the label here, so this is the black hole mass as a function of time and as a function of redshift here. Here, redshift 6, you have a black hole mass of about 10 to the 6 solar masses. So now, this is not one of the supermassive black holes. I will show one in a minute. But this is a normal black hole, the one that we would like to be able to study, because it's the normal object. It's not the exceptional 180 centimeters tall kid in kindergarten. Now, for this galaxy, what do we see? So here we have the total black hole mass. Here we start from a seed of about 10 to the 5 solar masses. And here we have the various paths for black hole growth. In red, we have shocked gas. We see that it's very subdominant. In fact, as I said, shocked gas dominates for massive galaxies. And this is not a very massive galaxy. It has a mass of about 10 to 9 solar mass at redshift 6, so you can think of it as a typical Lyman break galaxy at high redshift. Then we get, from bottom to top, mergers. So the green curve is gas that was driven towards a black hole by these merger-driven tidal torques, which are very effective, but they don't happen often. Yes? So this is a simulation run with gasoline. So it's an SPH code. The resolution is about 100 parsecs. So we have the merger simulation, same code, same setup, a 10 parsec resolution. This is about 100 parsec resolution.
How does this depend on the technique if you ran it?
I will show it's the next slide. Okay, so here we, that's the slide that I was talking about, but too early. Okay, so mergers are very effective dynamically, but they're not very common. And in this case, in particular, what we see that dominates accretion of gas is this cold gas that is coming directly from streams or in diffuse fashion. So in practice, we can divide this as an early phase in which definitely dominates the cold phase, and hot gas and clumpy accretion and mergers may be taking over at lower redshift.
Marta, I have a problem understanding this plot. How can the gas mass be considerably less than the black hole mass?
Because you start with a seed mass of about 10 to the 5.
Oh, you put it in?
Yeah, the black hole forms with a seed mass, in this case 10 to the 5, and then everything else goes and adds on.
But even then, the difference should be 10 to 5 between
Yes.
the gas and the...
Oh, you have mergers of black holes as well, sorry. But mergers of black holes are not typically the dominant path all the way to the redshift 0.
Total gas reservoir in the galaxy must be considerably larger.
Oh yeah, absolutely. So this is only the gas that is actually going within the Bondi sphere and the influence radius of the black hole. So it has to go and get all the way to the center. This is in fact the gas that we know has low angular momentum compared to everything else. So if we go back to this plot, the gas that is actually accreted, if you look here, this is the gas that is actually accreted, this gas, you see here, this very, what I find here fantastic is really this combination of angular momentum and accretion. For instance, look at this phase. You have a constant gas mass. Here you have a high angular momentum, the black hole doesn't see it at all. So you can have a lot of gas, it's not really telling you anything about the black hole. Okay. So now going back to the different code. So here instead we are comparing this with an AMR code. This is Ramses. This is a more massive galaxy. So here we are approaching the type of galaxy that hosts a quasar like the one seen at Redshift 6 or 7. It's still a bit less massive. Technically is very hard to run a simulation with a very large mass and a very high resolution. The resolution of this simulation is about 15 parsecs and down to Redshift 6. So here what you see is, again, it's much more messy, but this is, again, the fraction of gas that is accreted onto the black hole as a function of the various avenues it can choose. So you have collimated cold gas streams. It was shown in blue in the previous slide. Cold diffuse gas, this was again shown in blue in the previous slide. And here you have hot gas, the hot gas which is shocked in the galaxy. Now, if you focus, let's say, just on the red curve over here, you see at early times when the galaxy is small, most of the gas that goes onto the black hole, like in the previous case, is driven by these cold gas flows. But as a function of time, when you go at later times, the galaxy grows, gas gets shock heated before reaching the black hole, and on top of it, you see here, so here is the gas of mass. Negative flux means the gas is going towards the galaxy, towards the black hole. Positive number, the gas is going out. So this is an inflow, this is an outflow. What is happening at this particular time? At that particular time is when the black hole starts becoming very active. If the black hole becomes very active, it inputs an enormous amount of energy, thermal and kinetic energy in this particular case, and it triggers outflows in the galaxy. So this is when I said earlier on that you cannot study, that studying this problem is really the problem is understanding how galaxies are able of doing this despite all the issues that they have. So this is an example. So this is the same simulation, the AMR simulation. And here you compare the gas property at redshift about 6 in a case where you have no black hole or where you have a black hole. Now here what I want to highlight is simply the differences in densities, shown here, and in temperatures. Now, when you have a very active black hole in the center, you input a large amount of energy. I gave you the example earlier on of the supernova in a tiny galaxy. This is a similar case. If you calculate the amount of energy that is released by growing a black hole and you compare it to the binding energy of your galaxy, you can see that the binding energy of the galaxy is much less than the energy released by growing the black hole. There is a beautiful, simple explanation in a review by Andy Fabian last year. So at this time, what we're seeing is that even if the galaxy is able to feed the black hole, eventually the black hole starts refusing to be fed. This is shown as in this growth of black holes as a function of time. This is the second simulation. So here, the original plan was to reproduce a black hole of a 10 to the 9 solar masses by Redshift 6. And there is a failure, as you see here. So here is the black hole mass as a function of redshift. Again, here the seed mass is about 10 to the 5 solar masses. It grows by accretion, some mergers. You see here this very constant gradient. This means that the accretion rate is at the black hole is accreting at the Eddington rate for the whole time. When it reaches a very high luminosity, it starts heating the gas in its surrounding. If you heat gas to decrease density, it's much harder for this gas to reach the very center, the parsec scales, where the black hole is accreting.
This feedback is kinetic, it's not radiative, right? You're taking energy from the accretion power, you're not coupling it radiatively, is that correct?
I'm not coupling it radiatively, I'm coupling it thermally.
Thermally, right?
Not radiatively.
Turn that off.
Yes?
Why don't you just turn off
Oh, that's the top slide, the top two figures. That's exactly what you asked.
But this what you're showing here is with AGN feedback.
Yes. I mean, if you don't have AGN feedback, you have, I mean, you can grow black hole to 10 to 11 solar masses. Now, I haven't seen one in my life, but maybe you have.
That feedback is an arbitrary tunable parameter.
Well, you're talking about it as a tunable parameter. I'm talking about physics. I'm trying to understand the physics that couples these things.
When you just add heat to gas, that's pretty physics.
Well, let me finish, and I will tell you what I mean. Okay, so we go back to this, our equation. So what we have said is that we have some ideas of the initial seed masses from about 100 to 10 to the 5 solar masses. Again, let's assume a very low relative efficiency. Now, the question is, how is a galaxy able to feed the black hole at the Eddington rate for the whole time? There are two questions here. One is the feeding. One is the feedback. Feeding is the first step, the part that I discussed. How much gas is a galaxy able to give the black hole? Feedback is whether the black hole energy couples to the galaxy or not. So let me finish here with just one final slide, which is my favorite exotic explanation, is that sociologically, culturally, there is very much against super Eddington accretion. But something that is not very often appreciated is that super Eddington accretion is not super Eddington luminosity. These are two different things. Radiation, as we were saying earlier on, radiation can be trapped. Basically, the photons don't have time to escape from the accretion disk. Well, the disk changes shape. Instead of being a thin disk, it's called a slim disk. There are fat disks as well, depending really on the geometry. In these cases, when radiation is trapped, the relationship between luminosity and accretion is not linear anymore. Usually, we always say that luminosity is epsilon and dot c squared. We do it for the sun. We do it for everything. In this case, luminosity scales as the logarithm of the accretion rate. So you can be 100 times super Eddington in accretion, so in the growth of the black hole, and only a couple of times super Eddington in luminosity. So highly super Eddington accretion does not imply highly super Eddington luminosities. This is because, again, as we were saying, this implies a low effective relative efficiency, much less than 0.1, which is a number that we all love and use at the whole time. And you really need very short periods of time at this type of accretion rate, 10 to the 4th years or so, to ease the constraints on this continuous growth of the black holes at the whole time. And with this, I will skip everything else and go to the conclusions, which, as I was commenting a minute ago, I am not giving any answer. I'm a scientist who is trying to understand the problem. So what I can say is that we have constraints, from the observational point of view, we have constraints only on the tip of the iceberg. These very massive, very luminous objects that are not the average object. So it's very hard to try to understand the global evolution of the population. In general, if we take these equations that I showed you, you can rule out that the initial mass of the seeds is less than a few hundred solar masses unless you allow for super Eddington accretion, as I just discussed. And third, feeding and feedback. Do we understand feedback at all? Shutting off star formation, which is the reason why feedback was invoked in many cases, shuts off black hole formation as well. So my whole point is we really have to study this in much more detail, looking at the physics rather than the parameters. Thank you very much.
So thank you very much for this very nice talk. And I open to questions. Let's first ask the students if they have any questions. So, there are no students' questions. There is.
So, going back to this feedback mechanism.
Could you speak up a bit?
Yeah, going back to this feedback mechanism that you showed. So, there's a parameter of the amount of energy that is coupled to this one meter. Is that used to reproduce
luminosity functions, yeah. So the way we tune parameter, this parameter is for cosmological simulations with this luminosity function of AGN, the mass density of black holes today, the MC relation, and for merger simulations it is to reduce the MC relation at the beginning and the end of the simulation. So now, yes, once you have fixed that parameter, then you use it to make all the other simulations and predictions. My impression is, in fact, feedback has been overestimated in terms of importance in all this, but clearly it has to be modeled in more than one parameter.
In real data simulation, you don't really need in real data formation simulation, you don't really need pictures.
I completely agree with you. The problem is that these quasars exist. They have this emission, they have this kinetic and energetic power. What we have to understand is how that couples or not couples to the galaxy. So it's really about the physical process. It should not be a free parameter.
Okay, further two questions. So now let's go to the non-student question. Okay, yes.
You never mentioned the creation of God.
Yes.
This would what about that?
You can have some, so dark matter we expect is mostly collisionless. And at the very center, the densities are related typically by variance. So you can have dark matter accretion. We don't expect, based on density profiles of gas, to be the dominant factor. So in the very center, dark matter is a small fraction of the total mass. But you can have, in the nice part, you can have dark matter spikes from black holes. So I can think, I like black holes more as tracers of dark matter rather than vice versa.
So, question open to everybody. So, are there any further questions? Okay, three and then. So let's go from bottom.
I'm wondering about your slide of the three pathways. I mean, you argue that you need cooling to get to supermassive sequence. I think I would clearly agree, but if you have too much cooling, then you have fragmentation. So I think in the end,
It's a fine balance.
middle standard than top end, because you need to turn the feedback down vertically. So I guess in order to keep the temperature up so that this is fragmentation, you keep the efficient rest high.
I completely agree. I mean, this is the fine balance. I mean, now there are people who are doing much better work than I am doing on all this. Actually, mostly in German. So Latif et al., for instance, have done very nice research. So my personal opinion is that we haven't reached a phase in which we can say that we can simulate or understand it yet. We need very specific conditions. So my main question to myself and to all the other people working on this is how often we actually have all these conditions. Analytically, we can make these estimates. In terms of simulations, where you have, for instance, gravity is much more natural, we haven't reached that phase. For instance, most simulations assume zero metallicity or assume a very high liquid background. So at the moment, we're in the phase in which we're assuming things rather than having them. So
I think you need electricity. If you have just a bit of net enrichment, you are effectively cooling and you're fragmenting like hell. So I think you're almost in zero.
So the way I typically describe it is that the inflow time must be much less than the defragmentation time. So this is the way I describe it. So the way I described about metallicity, that if you have no metallicity, you are probably in the most favorable conditions. The other question to have is how high the metallicity is so that you stop this from happening. Well, and then there's dust and graphite here with the comment.
So I go. You don't want to?
You mean what?
Yeah.
The amount of material that you accrete after mergers must depend on the angular momentum orientation of the two merging
Please go ahead.
I was wondering how the angular momentum of the galaxies you were simulating were oriented. I think the angular
So in this case, the movie that I showed you is progress pro. So the angular momentum of the two galaxies are aligned with the angular momentum. But then we run some cases of inclined galaxies, retrograde and prograde. So we tried several different combinations. So at fixed mass ratio, the variation in accretion and loss in black holes are not huge. So the mass ratio and the gas content plays a stronger role than others. However, the moment so the prograde, everything aligned case is the strongest in terms of the numbers. When you go outside that, the main change is that instead of having very strong bursts of loss of momentum, accretion, you have a smoother evolution. But at the end of the day, so when you go to the end of the simulation, you ask, okay, how much did the black hole grow? The difference is very
Is it
small.
because the dominant angular momentum source is just the offset
So
the impact parameter?
if you're looking at region of 10 parsecs, so you have to drive the gas to very small scales. So in some sense, the small scales decouple from the large ones. So the initial conditions, so it is prograde or retrograde, determine how much gas is lost during concentric passages, run pressure, all these things. But when you go to 10 parsecs, you have forgotten the large scale. So it's really, it becomes much more similar.
Is that the same in this pH?
We have done this on SPH, so I cannot tell. We are redoing this a subset of simulations with an AMR code to check because, yeah.
I wanted to ask you about the top point. You say only the tip of the iceberg is known. So seems to be one of the relatively few observational progresses has been not pushing the redshift of quasars in the last 10 years, but knowing quasars that are more connected down in black hole mass.
Exactly.
What has getting away from the tip of the iceberg taught us? That's not good to me.
That was the last part of the talk that I skipped. But so what we're so I will show you just one slide that I stole from Chris Whelan. So this is a comparison of the mass function of black holes at redshift 6, which is shown here, this solid line and this is. So this is the mass function, the estimated mass function of black holes at redshift 6 using some of the black holes that he found down to 10 to the 7 masses or so. Okay, this is the one at redshift 0. Now, we have mass functions of black holes, so let's compare this to the mass function of galaxies. So the mass function of galaxies at redshift 0 shifted by a factor of about 500 to compensate for the black hole galaxy mass is shown here as a dashed line. So at redshift 0, we see that typically black holes are about a factor of 4 times 10 to the minus 3 the mass of their galaxy. If you go to redshift 6, this is the mass function of black holes. This is the mass function of galaxies shifted by the same amount. So there is no match. So there is a mismatch between the shift in mass, between black hole mass and galaxy mass at redshift 0 and at redshift 6. Now, interestingly, what is suggesting here, in particular at low masses, not at high masses, is that the mass of the black hole is much less than this. So the mass of the black hole must be 10 to the minus 4 the mass of the galaxy. So this is causing a bit of puzzle because we know that for the most massive black holes, those that live up here, we're expecting this to be a factor of several more massive than 10 to the minus 3, based on the CO observation of the holes. So this is what I'm finding, that we're learning by going to lower masses. We start finding puzzles. And we can propose answers as well, but more data will help.
So are there any further questions? Yes, please go.
I was going to ask about, you started to talk with stellar black holes and then we went to mass black holes. What if there are some in between?
Yes, these are called intermediate mass black holes. They have been searched for many years. and there is not compelling evidence. So actually, one of the problems we have always, okay, we have 100 solar masses and then a huge gap at 10 to 5. All the mechanisms that I suggested for black hole formation leave behind some of these tiny black holes. So they may be leftovers. There may be stellar black holes that are more massive from mergers and so on. But at the moment, the way they were looked for, or the only relatively efficient way to find it, possibly finding them, is to look at ultraluminous X-ray sources. These are X-ray sources, point sources, not in the center of galaxies, so they cannot be AGN. And they also must have a luminosity larger than stellar mass black hole. Most of them, however, are explained by beaming, by in some cases superconductor accretion. There is one case, HLX, something, which hasn't been shut down as this is not an intermediate mass black hole. So at the moment we have one possibility of something in between. There may be more. They're very hard to spot because of the low luminosities. So it's an active field of research.
Okay, so no more urgent questions. Then I would like to thank Marta again.